Let's talk about some ways that you can make sure not that the variables are correct in your model, but that your model overall is performing well or how accurate your statistics are. This first one is one I've actually seen many students struggle with on the final project, and that's when you're doing logistic regression. So your goal is to predict probability for something. This scenario has cholesterol level. As it increases, the probability of heart disease also goes up. The question is, where do you draw the line for saying, yes, this person is at risk for heart disease? If you set it really low, then you're going to correctly catch everyone who could have heart disease. You're also going to catch a bunch of people who maybe wouldn't have heart disease. Somewhere in the middle, some people like 0.5. Now your probability of heart disease is higher than not. Or you could set the line even higher so that only people that you say are risk are people who are going to be getting heart disease. And if you've studied AUC curves, then you understand how you can look at this to try to see where the type 2 error versus type 1 error is balanced and pick a good spot on this curve that gives you a good amount of area. If you haven't studied those, just know that you can set the line for where you're making the prediction. And here's what I've seen a lot of students do in the final project. Here we're predicting yes or predicting no, and the truth was either yes or no, and the line has been set so that everyone is predicted as no. And there are most people getting a no. So this problem happens when one category or the other happens the most in real life. And you're saying, well, he got 830 predictions. Well done. Only 7 predictions were wrong. But look at your prediction. Predict no for everything? It's really pointless. Don't give the client a rule that says, predict no one has heart disease because most people don't have heart disease, and so you're right most of the time. That's not really what the client's goal is. The client's goal is to be able to find people who do have heart disease, but not too many. So if you have an entire row of predictions that's gone, you need to play with this line until you get something that's a little more useful. And in leverage points, we talked about run the model with or without that particular data point. That's the same idea that we're going to be doing here, except as we do each model for every data point, we'll see how the standard deviation adjusts, or maybe how missing data is affecting the model. And so you can see how much error there is in your statistics based off how much it changes if you have certain data points in or out. And you can upgrade that. Instead of doing it one data point at a time, you can do groups and bunches of data points. Randomize it and take a group of 4 or 5, and that'll give you another way of looking at how much your statistics would adjust or change based off the data that you select. And this is related to the idea of having a training data set and a test data set. What happens is you do the analysis with the training data, and then you see how well it works with the test data. Now, cross-validation would say, okay, do this again and again, but change which is test data and which is training data. Here, this is not the goal. The goal is to just be able to test, does our analysis work based off this piece, and then you have something you can test it on. Why wouldn't you use the entire data set and then test it on only the test data? The answer is then the test data helps make the model. Of course, the model is going to do a good job of predicting the test data. If you're interested, Kaggle actually does this. They'll give you a data set and say, make a model, and then they'll test your model against their test set. What would happen if somebody made their model based off the test set? Well, of course, it's going to look like it works well. You give me 100 rows of data and ask me to make a model that can predict those 100 rows of data. Boy, I can do a really good job at that. And as you can see, people have done that. It is considered cheating, and sometimes there's actually ways to get away with it if they declare you the winner. And this one has a really sad puppy face, so you should feel like people who do this are really evil. Remember the lesson on ethics. Bootstrapping is a upgraded version of this. The bootstrap story, based on an old English story, based on an old German story, where this guy is like in a lake or a swamp, and he has to get out, and he can't, so he grabs his own bootstraps and lifts them out, and that's how he's able to get out. The physics doesn't actually work. It's meant to be like funny, but the analogy is there a way to pull yourself out of the problem? And that's what his method tries to do. It's an upgrade from the training test data because we're not separating the data and using smaller pieces of it. If you look over here, you can see other ideas for what to name it. The idea is we have this data and we grow it by duplicating the data several times and then sample from that back to our original data size. When I first learned this method, I got in a fight with the teacher. I'm sorry, Dr. Blades, but I was like, you can't just duplicate your sample and pretend you have more data. But that's not what's going on here. You don't run your estimates on the inflated, fake, improved data. It's down here where you've sampled little data sets of the same size, and then you can compare the statistics across those to see how your estimates, for example, of the variance or of the mean would change. Let me show you a picture. So here's our sample. It looks like it's right skewed, and then we randomly sample out of these data points with replacement, kind of like having this sample duplicated a million times and then drawing out of that. And here was one sample we got from that, and another one, and another one. Notice they're all somewhat right skewed, which fits because we're drawing out of this data, but all four of these are going to be a little bit different. They all give us slightly different estimates of x bar, and then we can look at the variance here and get a feel for how much variability there is in x bar. This is non-parametric. We actually pulled data points out of the pool of data sets. You could go to a semi-parametric where the data helps you find, for example, in this case, the mean, and this looks kind of chi-squared-ish, so we're going to give it a chi-squared with that mean that matches the data. And then again, we pull 4 data sets out of here from the distribution, not necessarily from the data. That gives us different estimates. Why might this be better? If it really is chi-squared, then yeah, this is going to give us better estimates. If, of course, it's not chi-squared, then you're going to have problems because you're making assumptions that aren't true. But it's really smoothing over the data you saw before. Full parametric, the degrees of freedom here, 3, are coming from this x bar is probably an estimate of the average. And so we just come up with a distribution that seems to be matching the kinds of distributions that give us the estimate we got. And then from each of those, we're getting different x bars. None of these x bars really match the 2.87 we saw, so the parametric bootstrap makes me worry a little bit here. I was okay with semi-parametric, but this one seems to me we've gone too far. And if you make assumptions about the distribution and they aren't true, then yeah, of course you're not going to get great results. These are all related to the idea of resampling, which is a really broad term. People can use that in a lot of different ways. Parametric resampling is a type of that where you have parameters that you're getting a distribution from. Jackknife is somewhere in between as you are resampling the data. Is a parametric, but you're calculating statistics. You've got bootstrapping, which is related cross-validation and training and tests, so lots of different terms. The idea is you need some way to shake up your data and see how much your statistics move. And we didn't talk about permutation tests, but that's also another one that you could look into. I guess that would be the non-parametric version of the parametric resampling. I don't know why I have them overlapping. They probably shouldn't. Speaking of shaking up the data, let's imagine we have these data points and we've made a regression line, but we think there's error in the x values. We don't exactly know how much error or what it should be, so what we're going to do is we're going to give extra error to these x values. And they're all kind of moving in a nice dance because, well, frankly, it was hard to make animations. Okay, so this is the best I can do. It looks like they're all moving about the same, but in real life, each one would have its own random variation. So some dots going pretty far and some dots not so far. If you do that, the dots are going to be more spread out. So you'll get an estimate for the regression line that's a little bit flatter. And if we make those dots have even more error, then you'll get an estimate that's even more flat. You can then look at those and say, all right, if this was how flat I had with lots of error, a little error, here was my original data. If I had no error, then it would be up here, following that pattern. That's the extrapolation part of the simulation extrapolation for Simex. So this is a way of trying to estimate, here's how much error I think I have in my x values. This is the regression line I should have been getting. And of course, this idea can extend to even more complicated models. And it's not an unusual practice for advanced statistics to say, let's introduce error And as we introduce more and more error, we want to play with what's happening to our model. So we've mentioned a bunch of validation methods. I'd like to hear in the discussion board, what kind of methods do you think you're going to be using? You're not necessarily locked into it because later you might decide, oh, there's something else that actually works better. What ideas do you have for validating that your model is working well, and what methods do you plan on using? Speaking of the final project, this video emphasizes right here model validation, which is part of the rubric that you have done something. For most people, probably residuals. If you're doing logistic regression, that confusion matrix, or something to say that you're checking whether your model is working well. Keep in mind, it even says in the syllabus, our goal is more about communicating to the client instead of going into depth about how bootstrapping and resampling methods require, regularity conditions and all that stuff. No, explain to the client what you're doing and then help them understand that you have something that is good. It often doesn't need to be very long. Just saying that we have checked the model and using cross-validation, we believe that our model is valid and working well. Here are some main elements. It's not like you need to follow this, just an idea of some of the pieces of your report that you might need to write about. Statement of research, or, like introduction, why do we care, what makes this important? Study design, how did you pick the data and where did it come from? Which statistical method are you using? Results here, explain this. This one's really important, so it looks like it's only 1/5. It's probably going to be a lot more than that. Then we have conclusions. What was it the client wanted you to answer? And tell them what it is they wanted to know. So for the video post this week, this first part, statement of research, what makes your project interesting? Keep in mind, we're not talking about what makes the statistics interesting, what makes the research interesting. We're saving bees because we like honey on our toast, or we're trying to predict housing prices because this will help people understand what houses they should buy and money and a place for their family to be. Tell us why your project should be interesting to people who don't know statistics.